All right, get ready, because in this deep dive, we're tackling a real head-scratcher, dark photons. It's like there's a whole other side to the universe we can't even see, and these things, these dark photons, might just hold the key to unlocking it.
You know, that's a fantastic way to put it. We really are talking about a whole realm of particles and forces beyond what we experience every day. And, even a tiny discovery in this field, it could completely change how we understand the universe as a whole.
Now, you sent over some research, and full disclosure, the title was a bit intimidating, even for me. Revisiting Dark Photon Constraints from CMB Spectral Distortions. I'll admit I had to do a bit of reading to refresh my memory on some of the physics terms.
Oh, I can imagine.
But the main idea, if I'm getting this right, is that it uses the cosmic microwave background, that faint afterglow of the Big Bang, to try and hunt down these elusive dark photons.
Yeah, and it's kind of mind-blowing when you think about it. I mean, imagine using light that's been traveling for over 13 billion years to study something that's completely invisible to us. It's like using ancient starlight to piece together a crime scene, but from the very beginning of time.
Okay, so before we dive into the how, let's talk about the what. What exactly is a dark photon?
So think of it like this. We know that regular photons, those are the particles that make up light, right? Well, a dark photon is kind of like its ghostly twin in a way. It carries force just like a regular photon, but instead of interacting with all the stuff we see around us every day, it only interacts with this mysterious thing we call dark matter.
So it's like there's this hidden world existing right alongside our own, with its own forces and particles, and we're only just now getting these tiny glimpses into it.
Exactly. And the really exciting part is that this research might give us a new way to get even more of those glimpses.
Okay, so tell me more about these spectral distortions they're looking at in the cosmic microwave background. How does that help us find something that's invisible?
Okay, well, imagine the CMB, for a second, as this perfectly smooth, very faint hum of energy that's spread out across the entire universe, right? Now imagine something comes along and creates these tiny ripples or changes in that hum. Those are the distortions we're talking about.
So it's kind of like if you had a perfectly tuned radio signal, and then suddenly there was some interference messing it up.
That's a great analogy. And basically what these researchers are saying is that dark photons, when they're born, they might actually be causing some of that interference.
Hold on, when they're born. So how do these dark photons even come into existence in the first place? They don't just appear out of thin air, do they?
You're absolutely right. They need energy to come into being. And what this research suggests is that they might be actually taking that energy from the regular photons in the CMB, almost like a cosmic battery drain.
Wow. Stealing energy from the afterglow of the Big Bang, that's something else. So by looking for these tiny dips or changes in the CMB, they're essentially trying to catch these dark photons in the act.
Exactly. And here's where it gets even more interesting. Not only might dark photons be taking this energy, but they could also be messing with something called entropy in the early universe.
Entropy. Okay, now that's a term that always throws me for a loop. Can you break it down for me?
Sure. So think of it like this. Imagine you have a perfectly organized room, everything in its place. That's an example of low entropy. Now picture that same room after, say, a football team just finished celebrating a big win in there. It's a lot more chaotic and disorganized, right? That's high entropy.
Okay, I think I'm starting to get it. So how does this relate to dark photons in the CMB?
Well, in the very early universe, just fractions of a second after the Big Bang, things were incredibly hot and dense, very high entropy. But as the universe expanded and cooled, things started to become more orderly, lower entropy. What this research suggests is that when dark photons steal energy from regular photons, they might also be increasing the entropy of the early universe, just a little bit. It's like the universe is trying to tidy up, get everything organized, and these dark photons are sneaking in, messing things up a bit, making it harder.
Okay, that makes sense. But here's what I'm wondering. If these distortions are so tiny and they happened billions of years ago, how can we even be sure they're not just getting lost in all the noise of the universe? I mean, it's a big place out there.
That's a really important question. And you're right, the CMB, it's incredibly faint to begin with, and these distortions even fainter. But that's where this research gets really impressive. These researchers actually created this incredibly detailed computer model to simulate the entire evolution of the CMB, including the effects of these dark photons.
So they basically built a virtual universe in a computer just to see how these dark photons would mess with things.
Yeah.
That's some serious next-level science right there.
It really is. And here's the key. By comparing their simulations to the actual data from telescopes like COBE and FIRES, these were the telescopes that gave us the first detailed maps of the CMB, they could start to figure out some limits on what these dark photons could be like.
What do you mean limits? Like how heavy they can be or how often they interact with regular photons?
Exactly, you got it. They found that previous studies had actually underestimated how much energy these dark photons could be taking from the regular photons. And this new research, it actually narrows down the possible characteristics of dark photons, which is huge, especially for future experiments that are going to be trying to actually detect these things.
Oh, I see. Okay, so it's like this research is giving us a much clearer target. It's not just a shot in the dark anymore. We actually have a better idea of where to look.
That's a great way to put it. And it gets even better. This research, it doesn't just help us find these dark photons, it also has some really interesting implications for understanding the very early universe, right after the Big Bang.
Now that is where it gets really exciting for me because I love hearing about how these discoveries connect to the bigger picture. So tell me, how does looking at these tiny distortions in the CMB tell us anything about the universe's like baby pictures? What was going on way back then?
Well, it all comes down to this thing called the energy balance of the universe. Think of it like this. The universe, right after the Big Bang, it had a certain amount of energy to work with, and that energy, it got distributed amongst different particles.
Yeah.
There's this really crucial number called Neph. You can kind of think of it like a cosmic recipe that tells us about the energy balance in the early universe. And if the ingredients, like the different particles and how much energy they each had, if those weren't just right, the universe wouldn't have evolved the way it did to become what we see today.
Okay, I think I'm following.
So, if dark photons were stealing energy from regular photons in the very early universe, it would have affected this Neph number, changed the recipe just a little bit, you see.
So by studying these faint distortions, these whispers from billions of years ago, we're basically checking the universe's math from its earliest moments.
Exactly. And this research, this gives us a completely new way to measure that Neph number, which means we can compare it to what we expect based on our understanding of the Big Bang, to see if everything adds up, to see if we're on the right track.
Okay, so it's like we're using the cosmic microwave background as this cosmic accounting ledger. We're going way back to the beginning to make sure the universe balanced its energy budget right from the get-go.
That's incredible. It really speaks to how clever cosmologists can be. They've found a way to look back billions of years using these really subtle signals in the CMB. And the best part, it has the potential to completely change how we understand those very first moments of the universe.
Now, you mentioned neutrinos earlier and how Neph is affected by them. Those are some pretty weird particles, right? I mean,
Yeah.
What exactly are they and how do they play into all of this?
You're right. Neutrinos are definitely some of the most elusive particles out there. They're incredibly light. We're talking almost massless. And they interact with other matter so quickly that trillions of them are passing through your body every second and you'd never even know it. But even though they're kind of ghostly, they were still a crucial part of that energy budget in the early universe, you see.
So if dark photons were messing around with the energy balance back then, it would be like throwing off the recipe, even for those ghostly neutrinos.
Exactly. And that's why measuring Neph is so important. It's like checking the universe's recipe book to see if all the ingredients are in the right proportions. And if that ratio of neutrinos to other particles is off, even by a little bit, well, that could point to some new physics we haven't even begun to understand yet.
So this is seriously mind-blowing stuff. So let's recap for a second just to make sure I've got this straight. We've got these dark photons that might be stealing energy from regular photons in the CMB, and this could tell us where to look for them. A and D give us clues about the universe's energy balance right after the Big Bang. It's like this research is pulling back the curtain on two mysteries at the same time.
I like how you put that. It really highlights how interconnected everything is in cosmology, By studying one thing, in this case, these tiny distortions in the CMB, we can unlock secrets about the fundamental particles, the evolution of the universe, and maybe even the true nature of dark matter.
It really makes you wonder what other secrets are still out there, hidden within that light from the cosmic microwave background, just waiting for us to uncover them.
Absolutely. It reminds us that we're really just scratching the surface when it comes to understanding the universe and all its wonders. It seems like with every new discovery, we just have more questions. It's this incredible journey of exploration.
Well, on that note, I think it's time to wrap up this deep dive. But before we go, I want to leave our listeners with something to really think about. This research gave us some really exciting new clues about dark photons, but it also showed us how much we still don't know. And that's really exciting. There's so much more to discover. So here's a final thought. If dark photons are really out there, shaping the universe in ways we're only just starting to grasp, what other effects might they have? Could they be influencing the formation of galaxies? Could they even be interacting with us right now in ways we haven't even imagined? The universe is full of mysteries, and it's up to all of us, these curious minds, to keep exploring. Until next time.